The boundary of survival for an abandoned combat aircraft is strictly environmental. On Taroa Island within the Marshall Islands, that boundary was breached decades ago. The objective in the early 1990s was the forensic extraction of rare Mitsubishi A6M3 Model 32 remains from a bypassed forward airfield before tropical consumption erased the airframes completely. The Sterling brothers' recovery effort centered on the substantial remains of two aircraft, later identified around serial numbers 3148 and 3145. The operation would test both improvised transport and the remaining strength of metal that had already spent decades in a tropical battlefield. The Mitsubishi A6M3 Model 32 was an evolutionary step in Japanese military aviation. Manufactured in 1942, this variant was deployed across the Pacific Theater to address specific combat requirements. Earlier carrier-based Zero variants used folding wingtips for aircraft carrier stowage and preserved the long range for which the type became famous. On the Model 32, Mitsubishi eliminated those folding tips, creating the distinct, clipped, squared-off wing profile. The change shortened the span by roughly 3 feet and altered the aircraft's handling. The shorter wing was associated with quicker roll response and improved diving characteristics, but the reduced wing area cost the Model 32 some of the range and turning performance that had defined earlier Zeros. That limitation mattered in the Pacific, where distance could decide whether a fighter was useful at all. Rather than treating the aircraft as a pure long loiter machine, Japanese operators used the Model 32, where its speed, climb, and local defensive value could still be exploited from forward airfields. This specific performance envelope dictated where the aircraft were stationed. On Taroa Island within Malwelap Atoll, the wartime airfield served as a remote staging point for interceptor squadrons defending the perimeter. The operational life of many of these airframes ended not in the air but on the ground. Allied forces isolated Malwelap during the island hopping campaign, and Taroa was subjected to sustained bombing and shelling. Aircraft were destroyed, disabled, or left behind as the base lost its ability to function as a supplied forward air station. By 1944 and into 1945, the garrison was cut off from external supply chains, and the wrecked aircraft remained on the island as the war moved past them. The conflict ended, but the physical degradation of the machines accelerated. The dense vegetation quickly enveloped the parking areas and the old airfield margins. The wrecked fuselages remained hidden under the thick canopy for decades. In 1991, the John Sterling recovery team arrived on the atoll to extract the surviving wreckage. The team encountered immediate logistical constraints that dictated every subsequent handling decision. Taroa Island is an isolated coral structure. It had once been a major wartime airbase, but by the recovery period it did not offer the usable modern port, road, lifting, or workshop infrastructure that a conventional aircraft recovery would require. The objective was to retrieve the massive combat airframes, but the practical extraction path was obstructed by vegetation, wreckage, and the limits of the island itself. Moving the hardware required cutting a workable hauling route from the jungle interior toward the shoreline. At the water edge, the team met the next operational boundary. The confirmed recovery record is stark enough without adding unsupported machinery. After months of negotiation and fieldwork, the wreckage had to leave the island as controlled cargo despite weight, awkward dimensions, and compromised structure. Every lift, drag, pack, and transfer risked destroying the artifact value that made the recovery necessary. How does a recovery team move intact combat airframes through dense tropical vegetation without destroying their remaining structural value? A combat aircraft's wingspan imposed a fixed clearance radius. On the jungle route, that geometry, not simple weight, forced the next decision. After 45 years of exposure, preserving a recoverable evidence meant reducing the aircraft's footprint rather than forcing an intact move. The consequence was structural. The airframe would have to be reduced into transportable sections. The atoll imposed an aggressive marine corrosion regime. Under the vegetation cover, trapped moisture created a persistent, high-humidity microclimate around the wreckage. This moisture was constantly saturated with salt spray carried inward from the adjacent ocean. The combination of salt, water, and tropical temperatures created a perfect catalyst for metal degradation. This environment specifically targeted the metallurgical composition of the Japanese airframes. Mitsubishi engineers originally constructed the aircraft using extra superduralumin. This specific aluminum alloy contained a high zinc content. When manufactured, the zinc additive provided an exceptional strength-to-weight ratio necessary for high-performance combat maneuvers. However, under prolonged exposure to the corrosive marine environment, this high zinc concentration became a massive liability. The damage did not stop at the outer surfaces of the skin panels. In high-strength aluminum alloys, chloride-rich marine exposure can promote localized attack, including intergranular and exfoliation corrosion along vulnerable grain structures. Over decades, a recognizable part can lose the dependable strength required for flight. These components had ceased to be airworthy structures. They were fragile historical shells, valuable for identity and geometry, but unsafe as primary load-bearing aircraft parts. This loss of material integrity removed the option of clean factory-style disassembly. Bolts, rivets, and mating surfaces had been fused by corrosion, so reducing the aircraft's footprint required a harsher intervention than unfastening and lifting intact assemblies. The recovery team executed a destructive extraction to save what remained of the artifacts. The clearest surviving record shows that the wings from serial number 3148 had been sawn off near the root, presumably to ease transportation off the island. That act sacrificed the structural continuity of the original wing, but it reduced the airframe into sections that could be moved through the available recovery path. The precise tool, blade path, and internal structures cut during the operation are not documented in the public record, so the safest account is also the simplest one. The wings were cut near the root, and the wreckage was moved out in pieces. After the destructive extraction, the severed wings, fuselage sections, and corroded tail components were secured for shipment to the United States. The move halted the atoll's environmental consumption, but it also delivered a fragmented evidence set: heavy, cut aluminum with uncertain identity and no immediate structural cohesion. Before reconstruction could begin, investigators had to establish which combat lineage each major section belonged to, because mixing incompatible variants without provenance would undermine both geometry and safety. The forensic identification process focused on the evidence that had survived the island. Investigators searched the wreckage for serial evidence, painted markings, part numbers, and manufacturing clues, then compared those findings against archival research. The damaged exterior skin panels could not tell the full story on their own. By combining the surviving physical evidence with historical records, researchers established that the restored Zero was not the remains of a single untouched aircraft, but a reconstruction based primarily on major components from multiple airframes. Through this careful sorting process, the team isolated the strongest foundation for a flyable reconstruction. Current museum research identifies the forward fuselage and wings as coming from serial number 3148. The rear fuselage and tail are identified with serial number 3145. This created a new engineering boundary. The team possessed enough major structure to reconstruct a complete Zero, but the principal sections came from two different wartime airframes, and the museum notes that their exact wartime relationship cannot be stated with certainty. Before any metal cutting or structural mating could begin, technicians had to extract another layer of historical baseline data from the corroded shells. The exterior surfaces of the wreckage were heavily weathered, and surviving markings could not simply be read as if the aircraft had just left the factory. To guide the final finish, technicians relied on the best available evidence: protected paint remnants where they survived, remaining markings, photographs, comparative research, and known Mitsubishi production practice. This work established a defensible restoration finish rather than a guess based only on degraded external surfaces. With the historical data secured, engineers faced the primary physical constraint of the fuselage reconstruction: mating the forward section of serial 3148 with the rear section of serial 3145 required absolute geometric control. These fuselages were manufactured independently and experienced different operational loads during their service lives. Furthermore, each section had warped and twisted differently during the long abandonment. Simply joining them at the available mating frames would introduce fatal aerodynamic instability. Any slight deviation in the center line would misalign the engine thrust vector and disrupt the angle of incidence on the tail surfaces, rendering the aircraft uncontrollable in the air. To enforce dimensional control, the restoration relied on precision fixtures, careful measurement, and the accumulated experience of the rebuild team. Engineers and technicians established a continuous centerline, controlled twist, and verified that the fused fuselage geometry could support safe flight. The fixture work produced a practical, documented axis for future flight operations without claiming impossible zero tolerance or perfect factory geometry. With the fuselage baseline established, how do engineers reconstruct wings that were permanently sawed in half decades ago? The next recovery limit was how to transfer flight loads after the original spars had become evidence rather than structure. Legend flyers in Everett, Washington treated the historic components as master references, securing them on benches, and pairing their surviving geometry with drawings, measurements, and known zero construction practice. From that evidence, workers shaped fresh aerospace-grade aluminum into frames, stringers, ribs, spars, and skin panels that preserve the Model 32's external profile and internal geometry while meeting the practical demands of a flying warbird. The severed wing sections required separate load path work. Because recovery had broken the original continuity, technicians treated the surviving wing shape as a pattern, then built new flight-rated members to carry bending and torsional loads and restore the clipped zero profile in flight. As the freshly stamped aluminum components were systematically riveted together, the structure transitioned from a collection of corroded artifacts into a viable, rigid airframe. The exacting fabrication work spanned several years, requiring immense technical oversight to ensure every new piece integrated flawlessly with the newly aligned fuselage. During this fabrication period, the project's organizational path shifted from a long Legend Flyers rebuild to museum-backed completion. Legend Flyers had acquired the project in 2011 and spent more than a decade pushing it toward flight. The Military Aviation Museum became involved in late 2020 when the aircraft appeared visually close to completion but still required substantial systems work, then announced its acquisition of the rare A6M3 in 2022, bringing it into the flying collection for the final push toward test flight. By the time the museum took responsibility, the fuselage and wing assembly had a stable external profile and documented load paths. That solved the airframe problem, but propulsion forced a sharper boundary between historical preservation and flight safety. The original Japanese aircraft used a Nakajima Sakae 21 radial engine to generate thrust. While surviving examples of this power plant exist, an original wartime engine is a difficult foundation for routine flying. The incomplete Sakae associated with this project was not a simple, ready-to-install answer. Rebuilding it to airworthy condition would have meant confronting corrosion, missing or worn components, limited parts availability, and the high cost of making an 80-year-old combat engine reliable in modern operations. The team therefore moved away from the historically exact power plant and chose a supportable substitute for flight safety. To power the reconstructed airframe, the engineers selected an American alternative. They made the calculated decision to install a Pratt Whitney R-1830 radial engine. This specific power plant was widely produced, heavily documented, and utilized extensively in American aviation history. Its active support network gave aviation technicians access to certified replacement cylinders, carburetors, and overhaul services, making the engine a practical foundation for testing and operating the fighter safely, including overpopulated areas. Even though the R-1830 was close enough in size, weight, and performance to make adaptation plausible, similarity was not interchangeability. The team still had to make the installation behave as part of the Zero by resolving weight and balance, thrust and torque reaction, vibration, cooling airflow, propeller compatibility, cowling clearance, maintenance access, and load transfer into the firewall and forward fuselage, with the whole interface remaining inspectable before every flight. During this critical final assembly phase, the project required specialized oversight from several directions. Museum maintainers, pilots, and outside warbird specialists helped inspect and prepare the aircraft as it approached flight. Brad Pilgrim was among the experts involved during the late-stage preparation and inspection work. His participation added another layer of warbird experience, but the final readiness of the aircraft rested on the broader team's inspections, adjustments, ground runs, and test planning. The installation opened final verification. Ground runs exposed the kind of late-stage squawks a hand-built warbird can produce. Accessory adjustments, a propeller governor oil leak affecting blade pitch control, and temperature indications that had to be checked against direct measurement. Each issue had to be resolved before flight, but ramp testing could not reproduce the full airborne load case. How does an aircraft composed of 2 combat fuselages, new aluminum, and an American radial engine perform under actual aerodynamic load? An 83-year gap separated the aircraft's original manufacturing date from its return to aerodynamic pressure. On May 5, 2025, the static reconstruction phase concluded at Payne Field. Chief pilot Mike Spaulding took the Mitsubishi A6M3 Model 32-0 into its initial test flight, moving the machine from engineered display piece back into an active aircraft. The maiden flight had to map the hybrid airframe stability through incremental envelope testing, not a display of maximum capability. The pilot introduces gradual speed increases and minimal control surface deflections, then watches for uncommanded yaw, pitch instability, abnormal flutter, and cooling behavior under continuous load. Stable parameters allow the envelope to expand slightly. Any deviation requires an immediate abort and safe return to the runway. Spaulding advanced the throttle, and the aircraft accelerated down the tarmac. The wheels lifted off the runway, and the heavy structural mass fully transferred its weight from the landing gear to the newly fabricated wing spars. The initial climb out focused entirely on engine instrument verification and baseline handling characteristics. Spaulding established a steady, controlled climb rate, avoiding any aggressive maneuvering that could stress the unproven airframe. The test flight profile kept the aircraft inside a conservative operating area. Spaulding climbed to a reported altitude of about 4,200 feet, high enough to leave room for problem management while staying within reach of Payne Field and the chase aircraft. From there, he checked the clipped square wing's basic response without expanding the maneuver set beyond the first flight plan. The airborne operation was tightly bounded by time, roughly half an hour, long enough to cycle systems, capture critical telemetry, and watch steady-state oil temperatures under sustained aerodynamic load. It was also short enough to reduce exposure to latent problems, including a slow hydraulic leak or heat buildup inside the tightly packed cowling before the aircraft returned for inspection. Spaulding aligned the aircraft with the Payne Field runway and brought the Zero safely back to the ground, closing the initial post-restoration test flight. The short operation validated a major milestone in years of forensic engineering, but it did not end the test program. Further flights, inspections, and minor adjustments remained before the aircraft could be treated as a settled operational machine. The clipped wing Model 32 had cleared its first modern airborne proof point, showing that fragmented combat wreckage could be returned to controlled flight only through disciplined reverse engineering, careful substitution, and conservative testing.